Greetings. There's some questions on the homework I wanted to address. One, for example, was the, let me get my stuff up here so I don't have to multitask. There we go. One was a question on about the memberships and the trying to do e to the x. The entire purpose of that is to illustrate and have you have a little bit of hands-on experience with actually what the membership functions do in crafting the fuzzy regression machine response. And I think you can see with what you've done that if you twiddle the membership functions in some fashion that you get better or worse fits to e to the x. And I'm not asking you to optimize it in any sense. I'm asking you to look at changing some of the membership functions and convince yourself that indeed, yes, it makes a difference, and yes, maybe I can do an optimization if I put my mind to it, where I would do things mechanically, such as minimize the mean square error of the fit or some sort of thing. One of the things I asked you to do, so we could at least compare the results, was to check the mean square error of the results that you get. What is e to the 10, by the way? It's a big number, huh? 20. Wow, man, it gets big quick, doesn't it? Okay. How about that? You ever heard the old story of if you have this illustrates the concept of the exponential curve and the power of it. If you have a little BB in a very large stadium, and that BB doubles every certain time interval, and it doubles and doubles and doubles and doubles, and then exactly 1 year from when you started, the stadium is full of BBs. Get the idea? Question is, when was it half full of BBs? 1 second before midnight. So exponentials really go fast. I've always enjoyed that illustration. So that's what we have here, e to the x. What kind of mean square errors were we getting here? Somebody mentioned a mean square error of 20,000. Anybody get a better result than that? Anybody get a worse result than that? 200,000. See your order of magnitude better than his. Okay. So, yeah, be proud. Do you want to share us what your membership functions were? Or do you want to keep it a closely guarded secret? You just messed with the triangles. Okay. The FIS editor sounds like you're using the MATLAB software. Ooh, okay. You can do that if you want, but you don't need to. Okay. I think as far as programming, it's just a few lines of code, isn't it? It's not that bad as far as programming concerned. It's not something you need the MATLAB editor for, but if you want to use it, that's fine. And what did your first did you use triangular membership functions? The first triangle membership function. Let's just give people a start. We go from 0 to 10. Where was the first triangle membership function? Do you remember what it looked like at all?
Put a point, 0, membership of 1.
0, yes.
And then it started at 1.
Started at 1.
No, from the y-axis it's at 1. And then it goes all the way down to about 6.
Could you draw it? Come on up. That's your big chance on TV. So hide all the people on Channel 20.
And because on the exponential of what is it? If this is like 2.5 times 10 to the 4th. I can't get it.
Okay.
Then around 6 is where it starts to go up.
Yeah, and before that it's essentially 0.
Right.
Yeah.
Okay. At least on this scale. So then I just basically I call all of that very small. I think it was.
Mm-hmm.
And then I just this is where I just kept playing with it. But it was a variation of this. I think for that's 10.
So these are the membership functions that you did. That's right.
Yeah, pretty much. And that's was that small. Was it medium, big, or that was medium and big, or something like that. Medium and big. Yeah, that was very large. Or bigger and big.
Actually, it doesn't matter.
Yeah, doesn't matter. Anyway, that was my input, and then I had to play with the output membership functions too.
Okay.
And
oh, you played with the output membership functions also?
Yeah.
Okay. What do those roughly look like? Were they relatively uniform? Yeah, please.
I can't remember. Yeah, it was pretty close to this, I think.
be like
10 to the fourth. Okay. And so, since from 0 to 6, you want it to stay roughly, I think, pretty small. And then you want it to go up really, really fast, so then you put the last 3 triangles as close over here as you could. Like that, I think.
That worked really well for you.
Yeah.
Okay. Okay, excellent. Thank you. Thank you. Appreciate it. So if you didn't hear, this was the membership functions which were used for the antecedent, which we have a simple single value for the antecedent here. And it isn't unique, but it gave you that RMS error of about 20,000, which you're pretty happy with. Nobody's beat you yet, so we'll see what happens here. Okay, so hopefully that answers the questions on that. Are there any other questions on this particular problem? Can you see what we're doing actually and what the fuzzy system does? We went through the linguistic justification, but when we get down to things, basically the idea is how do we interpolate these triangles to basically fit these curves? That's what it boils down to. You'll notice another thing too on the defuzzification. This is very interesting. That I will bring to your point, and this is the weighted defuzzification. Where in one weights the consequent membership functions in accordance to whatever the weight was computed from the if-then table. And then what one does is you have these different weights. Let's call them weight 1, weight 2, weight 3, and weight 4. What's interesting about this is if we compute the center of mass, which is what we want to do now, the center of mass is going to be the summation of n is equal to, well, let me do it this way. It'll be weight 1 times the membership function for the first value plus weight 2 times the membership function of the second value plus, let me do 3. If I do 4, I got to write too much stuff down. Okay, it's this. So this is the function that we get when we add them all together, correct? So this is the sum, if you will, the sum of x. Now we would like to find the center of mass of this sum. Well, the center of mass of this sum, which we'll call m, is equal to the integral from minus infinity to infinity. Well, first of all, if we have a probability density function, which we don't, we know what to do in order to find the mean. We don't have the probability density function here because this does not necessarily have an area of 1, does it? Right? And we're familiar, at least in double E more than mechanics, of finding this. So in order to make this have an area of 1, what we do is we simply take the function and we divide it by its area, right? Say S of z dz. And this then becomes like a density function because this now has an area of 1, doesn't it? Right? And now in order to get the mean of this, we perform a integration and take the expected value. So this is the center of mass of that result. Make sense? Now, this being the case, notice that this becomes nothing more than the integral of s times s of x dx divided by the integral of s of z dz. And then if we substitute in these values, bear with me, I'm going to go ahead and use a summation term. We're all adults here. We can use summation sums. So x is going to be the summation of, say, n is equal to 1 to the number of values, let's call it capital N, of the weight of that value computed through the evaluation of the fuzzy regression machine times the corresponding membership function, dx, divided by the integral of the summation of n is equal to 1 to n of w sub n times mu sub n of x dx. Okay? So I'm simply making substitutions here and here. I guess this should be z's, but it really doesn't matter since they're dummy variables anyway. You following me so far in the math? It's pretty straightforward, just substitution. If we go up here, I'm going to continue this math instead of running off the board here. We're going to continue the math on the top, and we're going to say that the mean is equal to, and I'm going to rearrange these integrals now. We have the summation of n is equal to 1 to n of w sub n times the integral of x times mu sub n of x dx. And in the denominator we have the following. I've simply rearranged the integrations. I've rearranged the integrations and the summations. Very straightforward. Now, what is that numerator recognized as? Running out of space here. W sub n, what is this recognized as? Well, let's go on the side. Suppose that we take one membership function, mu sub n of x, and we would like to find the center of mass of that single membership function. What I maintain here, I'm going to have to erase this, I'm sorry, I'll redraw it though. What I maintain is that this integral looks a lot like the center of mass of a membership function, right? Doesn't that look like a lot like the center of mass? It's an equation for a center of mass, but it isn't, since that mu sub n, again, is a triangle. We don't know if it has an area of 1 or not. So we can get the center of the mass of the nth membership function by dividing this by its integral. I don't want to use w. What do I have left? Y. And then taking the center of mass of this. So see what I've done. I've taken the membership function, divided it by its area, so that this divided by this has a total area of 1, right? Then it's just like a probability density function, and I can take the center of mass of it by performing this integral, getting the first moment. Are you okay with that? Okay, this being the case then, m sub n then is equal to, well, we have the following. The integral of x times mu sub n of x dx divided by the integral of mu sub n of y dy. I got some colored markers. What is this equal to? What's a common name for that? If you were to tell your boss, what is that? That's the area of that membership function, right? It's whatever the area is. So let's call this a sub n. That's the area of that membership function, correct? So with this, we can take this stuff that we did on the side, all of this stuff on the side, and we can substitute in the numerator, and you'll notice that this other thing left in the numerator is up here, which we solve for is simply equal to m sub n times a sub n times the area of the membership function, right? Is this okay? And what's the denominator become? What is this? The integral in the denominator. That's the area of the nth membership function, so this is a sub n. So this is a simplification for the defuzzification. You don't have to compute integrals or areas or anything like that. The only thing that you need is the area of each of the membership functions and the center of mass of each of the membership functions. If you know the area and the center of masses of them, then you can perform this defuzzification to find the overall center of mass very quickly. Notice what this tells us indirectly. It tells us that the defuzzification is very insensitive to the shape of the final defuzzification membership functions. That if I choose defuzzification membership functions so that, say I chose 3 of them like this. This one has a mean 1 and a mean 2 and a mean 3. And this one has an area of A1, A2, and A3. So those are the areas under there. But I will get exactly the same results with these as if I choose a membership function, which is, say, for example, if I choose a membership function wherein we get something like this, and as long as the means, I can use Gaussians here or whatever I want. I can use anything I so desire there, and I'm going to get exactly the same results, insensitive to the shape of the membership function. The only thing that defuzzification cares about is the mean and the area of the membership functions in the consequent membership function, which is kind of interesting. Now, this is only applicable to the weighted method of defuzzification, wherein you take each of the membership functions and you multiply them by the corresponding weight. Remember also the technique where you clipped off the tops? That's different. You need to know the shape of the membership function when you clip off the tops. It's a different method of defuzzification, and it doesn't give us this very simple method of talking about things. Yes?
So was what Dick did with finding on the homework, were the weights included in that, or were they all weighted to 1?
For the membership functions, here's the point of the membership functions. If we could go over here. Here's the weight on the membership functions. This membership function he used, Dick, is that right? Okay. The membership functions that he used, this had a weight of M1, I'm sorry, a mean of M1, M2, M3, and we got to chop it off here somewhere, so say M4, okay? Those were the weights, and this had an area of A1, A2, A3, and A4, correct? My point is that if you use the weighted version, not the clipping off the top sort of defuzzification, but if you use the weighted version, you would get exactly the same result had you used a membership function looking like this that, well, it doesn't look like it has a good area, does it? That has the same mean and the same area, and you were to substitute one or more of those. It doesn't matter.
I understand
Okay.
your point. What I don't understand is whether or not those are weighted, what he drew on the board, or if they're just all 1.
Well, I think that normally when you begin with your membership function, I guess you didn't address which technique you use for defuzzification. Just drawing up these membership functions is not enough to specify the manner of defuzzification, because we could either weight these or we could clip them, right? Which did you use?
They're from 0 to 1 and use the centroid.
The centroid, but do you know if they clip them or they weight them? In other words, if you had this membership function and you had a weight of 1/2, maybe you don't know, it didn't come out in MATLAB. If you have a weight of 1/2, if you use the weighted method, you would come out with a membership function like this. If you were using the clipping method, you would have a membership function which looked like this.
That's what I used.
The second one, the clipping?
When you did view rules, as you moved it from 0 to 10, you could actually see it clipping.
Okay, so he used the clipping technique for doing that. Okay. But had he used the weighting technique, this A1 and this A1 would have given the same result. It would not using the clipping technique, because it's nonlinear. There's a nonlinear relationship of the way that it's cut down. Does that answer your question? Okay, good. Any other questions? Okay. How's the iris data becoming? Okay, that wasn't too hard. I swear, you look in papers today, classifier papers in PAMI or IEEE transaction systems, man, and cybernetics, IEEE transactions on fuzzy systems, where they do classifiers and clustering. They many times go back to the Fisher iris data and actually show that. It has become a benchmark of a data table on which to try things. Okay, any other questions on the homework then? I will be posting some more, hopefully today. I'm going to try as best I can today to do that. Okay, not doing that. Let's go ahead and let's return to the lecture. Let's remember what we did last time. Last time we looked at the Fisher discriminant, and I think we goofed up a number of things. Finally, in determining the ROC curve, receiver operating characteristic curve, we finally got that straight. Today I want to talk about a different type of distance, the Mahalanobis distance. I want to ask you a question before we get into the Mahalanobis distance, and that's the following. there's been kind of an assumption here when we had our points in this space that they are equivalent to each other in some sense. And in some sense, we're mixing apples and oranges. And I'll tell you why we're mixing apples and oranges. Because when we take this idea of the jockeys, here's the weight and here's the height, and the basketball players up here. And we talk about any line which separates these two. That is, if we choose a Fisher vector here, this is our Fisher vector, maybe we chose a threshold here. If we choose a threshold here, then this becomes a line which separates the jockeys from the basketball players, if this was the Fisher weight that we chose, or Fisher vector, okay? So remember, we chose the Fisher vector, and then we moved the threshold along the Fisher vector line, and depending on where we chose the threshold depended on our point on the ROC curve, our false alarms versus our detection probability. My question to you is that if this axis, which I believe in previous lectures we called y, what would be the dimensions of y? In other words, we know that the dimensions of the x-axis is weight, or pounds, and the dimensions of the y-axis is height in feet, right? Now, suppose that instead of this, here's my question for you, that we measured the weight in tons, up here it's pounds, but we measured the weight in tons, and we measured the height in angstrom units, okay? We can do that, right? Now, if we did that, the data would be graphically represented differently. My question to you is, would we get a different Fisher vector if we did this? If we change from height in, say, feet and pounds to height in angstrom units and tons. Do you think we get a different result?
What do you mean by different?
Do you think we get a different Fisher vector? That is, if for anything that came in here, okay, let me backtrack a second. Down here we do exactly the same thing we did before. That is, we compute a Fisher vector, and it might be different, okay? And we'll assume that we go out with this Fisher vector, and let's see, what would the Fisher vector be in this case? Angstroms would be way up here, right? I mean, we'd have stuff like this. There would be the jockeys. There would be the basketball players. Right? So in here, maybe when we computed the Fisher vector would actually go up here. Right? We compute the Fisher vector according to that formula. We come out here. Let's assume that there's some line here and some threshold which corresponds to here. My question is there a threshold which corresponds to here, which will give exactly the same detection performance? That is, if I bring in a basketball player and I give you his weights in, I bring in a person, I don't know what he is, and I give you his weight in pounds and heights, and I classify him by this as a basketball player, could it be that down here I would classify him as a jockey? In other words, will my classifiers be exactly the same in these two cases? That's what I'm asking you.
Each axis is only scaled by a scalar number.
Exactly. Yeah. The interesting aspect here is that each of the axes is scaled, and the way I drew it here is exactly the same as I draw it here. In fact, I could take weight up here, and in tons, I could put, I don't know exactly, but I could put something like 1/100th of a ton, 2/100ths of a ton. I could use the same exact axis, be it weight or otherwise, and the geometry then is exactly the same between the two. So the answer is yes, I do get the same result, which is very comforting for the Fisher distance. There are other techniques which don't have this dimensional aspect to them. And I will tell you one. Here is another classifier which you could use. Another classifier which you could use. This is more of a table lookup. Here's the table lookup. Here's the weight, and here's the height. And what we're going to do, I'll get good someday. What we're going to do is we're going to take all of the jockeys and we're going to take the center of mass. We're going to take all the basketball players, we're going to do a center of mass for each one of those. So we have a single point which is representative of the jockeys, the center of mass. We have a single point which is representative of the basketball players, a single point. And then we get an observation, and a guy comes in and the guy is this. And we have to announce whether that person is a basketball player or a jockey. One way to do this is to look at the distance between the 2 points and choose the one that's the smallest. Isn't that an obvious way of doing it? Right? But you'll notice here, if this all of a sudden becomes tons and this in angstrom units, these results can change. Because what's the units of this distance? Well, you're taking the square root of pounds plus height, which is feet squared. So that's the unit of that distance. What does that mean? Right? Now, there's a couple of ways to get rid of this. One is to perform normalization. Now, normalization, this is done for neural networks also. For normalization, you can either do the following. You can take the so-called z value, which is equal to the x value minus the mean of the class, divided by its standard deviation. So you would do this for all of the values of weights. So for example, the z value for weights would be the value of the weight minus the mean of the weight divided by the standard deviation of the weight. So I can even take off the omegas here. So this is standardly used, for example, in random variables to take something and make it into a density function with a zero mean and a unit standard deviation. It's very common. Well, this does the same thing with the data, for example. In the weight, you would do the similar thing for the height. You would take all of the height values, instead of using the height values, the nth height, for example, times the, divided by sigma n, you could do that. So does that make sense that we could use the z's and each of the z's, and now each of the z's equivalently have the same dimension, which is no dimension at all. But they're also related to each other in terms of their central tendency and their dispersion. Another way to do this is a maximum way of doing it, wherein we can take a result, let me call it the chi value, where we take the x weight minus the, I think it's the min weight, divided by the maximum weight minus the minimum weight. In other words, you do a search through your database and you find the minimum value of this vector and you find the maximum value of this vector. And you're going to take everything and you're going to squeeze it within the interval from 0 to 1. This will do it. Because you notice the minimum value, when xw is equal to the minimum, what is this? 0. When xw is equal to the maximum, what is it? It's 1. So it takes your entire data stream and it normalizes it between 0 and 1. And it's trying to do roughly the same thing that this thing is doing, which is trying to put things on an equal basis. And one can do the same thing for the height value. So you take the height minus the maximum value of the height divided by the, the minimum value. The maximum height minus the minimum height. So this puts things on a equivalent basis. Okay? And then it is this space where one can do a table lookup sort of procedure. There is an equivalent, not an equivalent, but a similar procedure which is also insensitive to the units, which doesn't use a Euclidean distance. Notice in essence what you're here is you're kind of scaling in a rubber band sense your weight axis and your height axis so that your spread in both dimensions is kind of the same. They're commensurate with each other. So you're doing a rubber band stretch. But notice this does not allow rubber band stretches around the 45-degree line. It's just the x line and the y line. Something that allows this more generally is something known as the Mahalanobis distance. Now, when we take the regular distance between 2 points in a plane, that of course is referred to as a Euclidean distance. The Mahalanobis distance is similar in concept, as we'll see. So let's take a look at the Mahalanobis distance classifiers, which we have here on the overhead. I want to show you my pretty slide. Isn't that nice? And here's what we're going to do. We're going to look at first the multivariate normal density. We're going to look at the contours. And from the contours, look at the Mahalanobis distance as defined, and then the minimum Mahalanobis distant classifier. The gifts for this, as for all of the things, are on the web page. Here is the basic idea behind the Mahalanobis distance. If we were to take the distribution of, let's say, weight and height of our jockeys and basketball players, I'm going to draw it a little bit different here. Say we had thousands of these things. And here we have the world's tallest jockey, and down here is the world's shortest basketball player. And I tell you, in certain cases, you're going to get crossovers. You might get something over here that's going to cause you a false alarm in some manner. The basic idea behind the Mahalanobis distance is as follows. I'm going to give you an overall sketch, then we're going to go into detail of where it comes from and show you how it works. Is to fit a family of ellipses to this cluster, so that these ellipses are best aligned with the data in some sense. Okay? And we're going to do a similar thing over here with this data. We're going to define a family of ellipses. The question, of course, is how far we define these family of ellipses. Then if we choose a point, if we get an observation point here, oh, and by the way, this corresponds to a contour of 1, 2, and 3 from the centroid. In a similar fashion, we have a centroid here. It's 1, 2, and 3. And each of these contours are a contour of equal Mahalanobis distance from the centroid. So instead of using Euclidean, which is kind of a bunch of circles, we're going to fit a bunch of ellipses and use the ellipses instead of a circular sort of relationship between them, and be able to do the classification that way. So for example, if we get an observation here, well, you notice the Mahalanobis distance is 2 units from this cluster, and it is 3 units from this cluster. Even though, notice how nice we've drawn it. So we would say that this is a jockey, right? Even though in the Euclidean sense, the way I've drawn it, doesn't that look closer to this than this? In a Euclidean sense, this is closer to this than it is to this. So if we were to use a Euclidean classifier, we would say, it must be a basketball player. Using the Mahalanobis distance, we would say it's a jockey. So this is the concept behind that. Now the question, of course, is how indeed do we perform this operation? We perform this operation, and I'm going to motivate it by appealing to your probabilistic knowledge. We do it by looking at the multivariate normal probability density function. And of course, we do not want to restrict ourselves to be in 2 dimensions. This can be in an arbitrarily large dimension. C over here is just a constant, and this constant gives, if it's a probability density function, it gives a total volume, a volume equal to 1. We're not going to be interested in that. In fact, what we're going to do, we're not going to actually go with this C. We're going to set this C is equal to 1 for reasons which you will see very soon. So this is the actual Mahalanobis distance, and the important thing to realize, and the important thing to remember from probability theory is the shape of equal contours of a multivariate Gaussian random variable, probability density function. You remember what they were? They were concentric ellipses, correct? That was the That was the overall contours associated with these. So if I were to look at this in 2 dimensions, I would have, first of all, a mean, which would tell me where this thing was centered. And then by this covariance matrix, sigma, I would get a value of ellipses, the spread and eccentricity of which corresponded to the detailed structure of this sigma value. In fact, if I set this to some sort of constant, you will notice that right at the mean, what's the value? 1? Or no, 0. No, I guess it's 1, isn't it? Right at the origin, it's equal to 1. And then as we go out, there should be a locus of values, which gives us a value of 2, a value of 3, and a value of 4, etc. So we actually get different contours with this. So the concept of the Mahalanobis distance is to fit this curve to the data. So we have a bunch of data here. And it kind of boils down to a probabilistic sort of estimate. It's kind of like this. We have some data which we have observed from a random process. We assume that that random process is a multivariate Gaussian. But we don't know what the mean is, and we don't know what the covariance matrix is. There should be a way that we can estimate the mean and the covariance. Just like in a one-dimensional case, we can estimate the mean of a density and its variance. In higher dimensions, we should be able to estimate the mean and the covariance. Of course, the mean, how do we estimate? Well, it's about equal to the average of all of the vectors. Don't yawn. Hurts my feelings. Right? Isn't this the mean vector? This is the average. And in a similar fashion, one can compute the covariance matrix, just the covariance matrix, by the sum of outer products. Now, in terms of, this by the way is, in terms of probability, that's the expected value of a random variable is equal to its mean. Sigma in general is equal to the expected value of x minus m times x minus m transpose. That's what the sigma is equal to. And we can estimate it just like we do the mean by 1 over n times the summation of n is equal to 1 to n of x sub n minus m x sub n minus m with a transpose. See, we've seen this sort of thing, by the way, where in the Fisher distance, haven't we? The same sort of sum of outer products. This appeared in the Fisher distance, the same exact result. So we can do this, and with this, determine the sigma and the m, which gives us our corresponding result. Now, the Mahalanobis distance is actually defined as follows. R squared is the Mahalanobis distance, is equal to, if we are given an observation, x minus the mean, times the covariance matrix inverse, times x minus the mean with the transpose on one side. This is the Mahalanobis distance. Do I have any people from India in here? Okay, I always check on the pronunciation. I think I remember this being the correct pronunciation from last year. Mahalanobis. Now, this is the Mahalanobis distance, and this is motivated, if you will, by these contours. Notice that the Mahalanobis distance, though, is actually a better distance measure than measuring the value of the density functions. Because you'll notice what happens when x is right at the mean. What is the Mahalanobis distance? 0, correct? When x is at the mean, the Mahalanobis distance is 0. So therefore, if you have an observation point, and that's what this x is, this is your observation, and you're trying to find out which class it's in. To find out which class it's in, you compare the Mahalanobis distance from this cluster to this cluster over here, which also has some things like this, right? You compare the two Mahalanobis distances. Well, what happens if that observation is right on the mean of this cluster? Well, the Mahalanobis distance from this cluster is 0 because x minus the mean. If x is equal to the mean, if your observation is equal to the mean of the center of mass, the Mahalanobis distance is 0. And you can see that as x deviates from the median, that we have these different contours, 0, 1, 2, 3, etc. In a similar fashion over here for this, we have values right at the center of mass at 0, then it goes to 1, 2, 3, 4, etc. So both of these will have a different Mahalanobis distance. Now, let me ask you this. If you have two ellipses like this in 2 dimensions, let me backtrack. Suppose we have 2 circles, family of 2 circles with centroid in 2 dimensions, and we look at the locus of points where the Euclidean distance, that is the distance from those 2 radii, is exactly the same. What curve do we get? We get a line, right? And in fact, that line is going to be the perpendicular bisector of the joining of the 2 centroids, right? That's what we would get using that. Now let me ask you, instead of circles, which gives you that perpendicular line, suppose we use ellipses. Can anybody give a conjecture of what the general form of the partition between the 2 bodies is going to be? It won't be a line, it'll be a curve. Okay. Can you be more specific? It'll be a quadratic, won't it? Because to get this result, we would equate this Mahalanobis distance for height to another Mahalanobis distance for weight, and we would equate the two, and I think you can see the only thing that's involved here is a quadratic. So in 2 dimensions, that means that separating this 2 in general for the Mahalanobis distance is going to be a paraboloid of some sort. That paraboloid can be a straight line. If you have 2 identical ellipses like this, right next to each other, the division is going to be a line. If you tilt one way, that line is going to bend into a parabola. In higher dimensions, it turns out to be a quadratic sort of separation. So the Mahalanobis distance is a straightforward generalization of the idea of Euclidean distances into higher dimensional spaces. The nice part about it is it is insensitive also to your choice of units, where a nearest neighbor lookup, where you get all screwed up with the units, goofs you up. You don't know what the units are for Euclidean distance when you have height and weight going this way. If you use the Mahalanobis distance, indeed, you get something which is unitless, because notice, what is the units? Suppose this was the Mahalanobis distance for weight. What would be the units of this? Weight, right? What would be the units of this? Weight. The result here, this inverse quadratic, performs an inversion on that to give the overall Mahalanobis distance a unitless value. So the Mahalanobis distance is unitless and therefore is not dependent upon whether you choose the result. So not only is it a generalization, but it gets rid of some of those problems that we have. Any questions on that? I wanted to speak quickly to an idea called the Curse of Dimensionality, which is another problem. We're touching on different aspects of classification, elementary classification, to lead us into the neural network. There's a problem referred to as the Curse of Dimensionality. You've seen the Fisher iris data, and there's an old expression. It used to be a philosophy, more is less. You ever heard of this idea, more is less? Anybody know what that means? What does it mean? Huh? Staples?
No, staples. I prefer more machines with less staples.
Oh, less staples is better than more staples?
No, a state machine, like a digital staples.
Oh, and digital staples. Okay. I thought you staples and papers. That's a good example there.
Okay.
You don't want 100 staples in there. You just want one. So you're saying states in the machine. Well, something interesting happens in classifiers in terms of... Does everybody know what he means?
Yeah.
Okay, what does he mean? Yeah.
More machine has less space than
More machines have less states.
There are 2 types, right? More and less.
Meaning.
Yeah.
Okay. I like the staples. So we'll take that. That's one that I can't understand. But here's something which is interesting. In classification, yes, typically more different types of features are better. For example, if you had weight and height of an athlete for jockey basketball player classification, that would be very nice. But if you had salary, yeah, that'd probably help you differentiate things even a little bit better. Okay. Now, there's certain things that if you put in there aren't going to be good at all, like eye color. I don't think. Would be something else that wouldn't matter? The degree of baldness. Length of hair. Okay. All of these would be inconsequential features. But let's assume that we're adding intelligent features such as salary and things like that. The problem is that the more features you add, even though they're useful features, the more features you add, the more data you're going to need to train your classifier. Notice in all that we've done in the Fisher discriminant function and the Mahalanobis distance, we have taken raw data and we have made from that raw data a classifier. We've made a classifier which allows us to give something that we haven't seen before to put it in one of two classes, either by the Fisher distance criteria or the Mahalanobis distance or even the table lookup, if we normalize our data correctly. So it takes data in general to design these classifiers. And the problem is that the number of features increases, the number of data that's required increases also. Let me illustrate the idea of the curse of dimensionality. Let us suppose that we had an underlying truth, and this truth in 2 dimensions was actually points within a circle or points not within a circle, and the circle being inscribed within a square. And just let me ask you heuristically, if I were choosing points at random in this square, how many points would I need to get before somebody that didn't know it was a circle could look at it and say, you know, I think, look, it looks like the circle is in the middle of a square. And you could get enough points to do that, right? That is, you could go, okay, point here, point here, point here, point here, point here, point here, that's out. Okay, that's out, that's out, that's out. That's not enough, right? If you just saw that, that wouldn't be enough. In fact, let me erase it to give you. That's not enough to see a circle, right? We need more. How about now? We're starting to see it, right? A little bit, maybe. Okay, now. Hey, we're starting to get an idea. I cheated a little bit. I recognize that. Maybe now we can kind of step back and squint our eyes and say, you know, those little circles look like they're outside of a circle. And we could actually guess that maybe this is a circle inside a square. But you can see there's a certain amount of data that we need to perform this characterization, right? Before we visually recognize it. Now, if I doubled this, it would become more clear, right? And I can do that. And then we ask ourselves, okay, for this two-dimensional problem, simple two-dimensional problem, how many points do we need randomly spaced before we can say, this corresponds to a circle within a square? I don't know, but I'm going to hazard maybe 100 points. Just for purposes of discussion, let's say 100 points. I think I probably have more there, but let's just say for purposes of discussion. So therefore, if I were doing the jockey basketball player thing, and it was classified like this, it isn't, I know that, but if we're classified like this, I'd need 100 people who are jockeys and basketball players in order to characterize the people within the circle from without the circle, right? Now let's add on salary. Suppose that I did this with salary. If I put this thing with salary, now I have weight, height, and salary. And let's suppose it's normalized now. Well, now all of a sudden I have a three-dimensional space to fill up, and let's suppose just for argument, just for pedagogical illustrative purposes, that now what I needed to do is I needed to differentiate between a spheroid and a box, which is placed inside a box. You get the idea? So now I have to build my classifier here based on data in accordance to observations. How many points do I need in order to differentiate that sphere from the box? Well, I think you can see that we can, at least roughly, maybe divide this box up into different slices. And I think that probably what we saw up here we could do to 10 different slices. And on each one of these slices, what would be the intersection with the sphere? It would be a circle, right? So each one of these slices would take about how many data points, if we learn from up here? Roughly 100. I'm illustrating a principle. I'm not trying to be rigorous now. And we have 10 of these. So in order to differentiate the sphere from the box, we would need about 1,000 different points. So you notice that because I have added the dimension of salary, I require a lot more data. And you'll notice that this is 10 squared, this is 10 cubed, and in general, a kind of a rule of thumb is 10 to the power of the dimension. Because this is the 2 dimensions, and this is 3 dimensions, and d dimensions. If we carry this onward, it would be that way. So you can see, in general, there's a reason that we would like to reduce the number of features to some salient, wonderful common denominator, if you will, in order to characterize our system to avoid this curse of dimensionality. There's a very happy result, too. And that happy result is that this curse of dimensionality is very conservative. It usually is not this bad. The reason it isn't this bad is because in many cases the data isn't dispersed totally. Rather, the data lies in a defined region or within a plane or some other sort of less obtrusive, expansive sort of space and can be characterized by much less than 10 to the d. Because I think you can see this is prohibitive. If you have 50 dimensions, go home, right? There's no way, unless maybe you're in subatomic physics, that you're ever going to get anything of that sort in terms of something to train a neural network or a classifier with, because you have a big space to fill up. There's also another way that you can do it, and that way is, this is something we call query-based learning, wherein one has a source of data. And one doesn't want the entire result, but one tries just to get results of data which is close to the boundary. I mean, if you just had data close to the boundary, your number of data goes down. And in fact, once you have this piece of data doesn't tell you nothing. That's bad grammar, I realize that, but I use bad grammar in order to make a point. This doesn't tell you anything because it's so far from the boundary, it's very obvious. I mean, this if a basketball player, this would be a guy 9 feet tall, okay? No way the person could be a jockey. It's very obvious that he's in this class, okay? So if we're far from the boundary, you don't have very much information. The information-rich data in a classifier is the one that is closest to the boundary. And the point closest to the boundary is usually data which has the maximum ambiguity. If you were trying to distinguish basketball players and jockeys, we had Muggsy, that short basketball player, right? He'd be on the boundary, okay? If we were trying to differentiate between trees and bushes, a bonsai tree would be on the boundary, right? Maybe even a false alarm that we couldn't even deal with. So there are these things which are of maximal ambiguity that exist near the boundaries. Now, you always don't have the ability to generate points on the boundaries, but sometimes when you're generating these points and you have control over the source of the data coming in, then you can do that. For example, you could put out a little announcement that said, I only want basketball players under 6'5" and jockeys over 5'5". That's all I want. So that then would limit the number of people you were sampled, and you would get samples closer around the edges because you don't care about measuring that guy. This is 9 feet tall. He's a basketball player. No doubt about it. So we have this curse of dimensionality, which we have ways of getting around, number one, and number two is typically more conservative than we need. There are actually two ways to get away from this. Let's see if I have it on here. Yes, show the pretty slide, the curse of dimensionality and feature selection. Ah, that's cute. Okay, we've talked about the curse of dimensionality. There are solutions to it. Also, some practical solutions is feature reduction versus feature selection. Let me explain to you the difference between reduction versus selection. Selection would be as follows. You have a catalog of 100 different features and you want to choose the 4 best. And the reason you want to choose the 4 best is that these features cost you money to do. Maybe you are running a quality, they cost you money to accumulate. Suppose that you're running a quality control line, for example, and as the products roll off the end, you want to classify them as successful or failures. Well, what you want to do is you want to choose as few tests as you can because each one of those tests is going to be multiplicative in terms of the addition to the price. Because the more tests you do, the worse it is. So you could do 100 tests and be 100%, or 100 features. You could have 100 features, be 100% correct, or maybe you could have 4 features and be 95% correct. Because you do get to a point of diminishing return. The question is how to best choose those 5 features. Doing that is referred to as feature selection. You take a big list and you choose a subset of the features. What is interesting in doing that is that you want to actually choose the best team of features. There was a classic paper by Cover at Stanford. It says that the best features, let's see, help me. Let's see, the 10 best features are not the best 10 features. Whoa. The best 10 features are not the 10 best features. It's kind of like putting together the Mariners last year, okay? If you get a whole team of great second basemen, you're not going to win many games in baseball, right? You need somebody to take over here and over here and over here. And suppose that you chose the 10 best players and they were all second basemen, you wouldn't have a good team. It's the same way in choosing the features. You don't want to choose the 10 best. The 10 best meaning all second basemen. You want to choose, or do I have it the other way around? You want to choose the best 10. In other words, you want to cover all of the positions in a nice way. So therefore, in feature selection, it isn't best to go down and figure out, this is the best feature. If I use this alone, I get 99% classification. Then go down here and you say, this is the second best feature, and with this one I get 98% classification, because with those two together, you still might only get 99% classification. You want to choose something that enhances that first feature's performance. And this becomes, if one is to do an exhaustive search among all the features, if you had 100 and you wanted to choose the best 5, you know how many you would have to do? This comes back from combinatorics. That's 5. Okay. Let's call it K. From N features. How many different combinations of K features do you have in N? Remember what it is? N choose K? So therefore, if you were to go through your set of features and you had data, which was a lot of data, and you wanted to choose the best 5 features, and you had 100 pieces of data, you'd have to choose 100, choose 5 different tests, and from all of those 100 choose 5 different tests, give the result that gave you the best result. And that's a lot of tests. That's very difficult to do. So the combinatorics kill you in searching for the best features. And you would rank them, for example, according to the ROC curve or some other sort of ranking characteristic. There are a number of different techniques which are suboptimal for doing this, and one of them is sequential selection. Sequential selection says the first thing you do is you go through and you choose the best player. You choose the best feature. That is the one by itself which gives you the highest degree of classification, highest accuracy of classification. Then what you do is you don't look for the second best feature, but you look for the best feature that plays with the best feature best. That makes sense? For example, you might choose the best feature, maybe Ken Griffey. And then you'd want to choose the second player that played best with Ken Griffey. Maybe, who's the right fielder, the bald guy? Buhner? Okay. So you choose the best feature, and then you choose the next feature. The next feature which works best with the first feature. Make sense? And so therefore, if you have n, you have to do n searches here. Because you have n features and you have to just search through them one at a time. And you choose the best one. Once you've chosen the best one, you put that on the side, and then you look at how each one of the remaining one plays with that one. So there's n minus 1 here. And so if you're choosing k features, down here you're going to get n minus k, so the result is going to be the total number of searches is equal to, at most, the product of these. That's how many searches that you're going to have to do, which is drastically less than the n choose k result. Okay? Yes? It should be a sum. Oh, you're right. Let's see. N, and yeah, you're right. Good. How's that? Something like this. This is the total number of tests you have to do. But as we found out, this is suboptimal because we got rid of Griffey and we did really good, right? So it wasn't good building the team around about the best feature and the best player. Rather, some of these lower powered features actually combine together to give you a better result. So this is definitely suboptimal. But it's the back of an envelope, a quick thing you can do in order to get a decent selection of the features that you want to use. Another very interesting way of doing it is by a process which is called dynamic programming. How many have heard of dynamic programming? 1, 2. Okay. Dynamic programming is kind of an intelligent search which allows you to search very large results, but be able to, in the process of exploring, come up with answers that allow you to throw away a lot of the other possibilities, thereby reducing your search. Sometimes, not all the time, but sometimes. So it's dynamic in the sense we don't know what we're going to search until we find it. We're going to go to a point, and then this point's going to give us a result, and this result might be so good that looking over here is totally ridiculous. I don't have to worry about it anymore. Let me give you an example for the feature distance. Now, here is what happens. You know what the Fisher distance is. What happens if you have, for example, a three-dimensional Fisher distance? Or let's be easy, a two-dimensional Fisher distance. So you have that in 2 dimensions, right? So you have the height versus the weight of the basketball players. You do the differentiation using the Fisher discriminant. Okay? Now, what is that Fisher, the Fisher discriminant, the metric that we will use to determine the goodness of the Fisher discrimination is the Fisher distance. Remember, that's the value of W, we chose the value of W in order to maximize the Fisher distance, the separation of the two by both the mean and the standard deviation. So that's what we're going to use to perform the separation. Now what I do is I have a Fisher discrimination of a two-dimensional function of height and weight of basketball and jockey players, and I have a certain Fisher distance. Now I'm going to add the third dimension of salary. Is that third dimension of salary going to increase or decrease the Fisher distance? It's going to increase the Fisher distance. Anybody else? Why do you think it increases the Fisher distance?
Because the distance is the sum of squares, which
Yes.
if you add one more dimension, you will increase.
You do increase the Fisher distance. So you make the discrimination better. Yes, because remember, a large Fisher distance is good. And yes, that indeed is the true result. Notice with 3 dimensions, you can choose that Fisher vector to totally block out salary. If you chose that Fisher vector to be orthogonal to the salary axis, then the salary doesn't even appear into it, and you could actually optimize with it orthogonal to the salary axis and get the same result as before. But the salary axis gives you another degree of freedom, which you can increase the Fisher distance even more. Yes, so adding dimension gives us the intuitive result that increasing the number of features increases the Fisher distance. So with that idea, we'll go into dynamic programming, and I think what we'll have to do is wait until next time, because I can't do it in 2 minutes. So with that, I'll ask if there's any questions. Okay, homework tonight, hopefully on the web, if not tomorrow. Check once a day, and I'll do my best to get it there. Thank you for your...
It's going to be due Thursday?
It'll be due Thursday, yes. Yes. I'll do my best to get it there tonight.
We're gonna add problems with this.
What?
We're gonna add.
What is today? Oh, never mind about the homework. I thought it was Thursday. Okay, we'll wait till Thursday. I'm a professor. Okay. You guys got to question authority. You've seen the bumper stickers. Okay, thank you for your attention. No homework.